Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 14, Part 1, Anova for completely randomized designs. So as a quick reminder, we are working in the scenario where we have our observed response, Yij equals mu plus tau I plus epsilon ij. This is essentially a situation where you have your experimental units, if you're not studying people, or if you're studying people, your subjects, and you randomize them into T different treatments. From there, you observe the response of each person under each treatment, right? And your goal here is to estimate the effects, or to ask yourself, is there a difference in these T treatments on some outcome variable? All right, in regular linear regression that we did in chapter 11 and chapter 12, we found that we could partition the total sum of squares. So we had a scenario where I was from 1 to n. We had the yi's minus y bar squared. That's your sum of squares total. We were able to split this into two pieces. The first piece was our yi's minus our y hat i's squared. That's our sum of squared errors. And our second piece was the y hat i's minus our y bar squared. So that was our sum of squares regression. So when we did that in those previous chapters, we could set up an Anova table by setting up regression, the source, regression, error, total. We were able to write out the degrees of freedom, the sum of squares, the mean squares, the F value, and our P value. So we could get our entire Anova table, right? And here we had our SSR, SSE, SST. And if you remember, our total degrees of freedom was n-1. Our error degrees of freedom was n-k plus 1. And altogether, this piece should have been k plus 1 minus 1, which leaves us at k. We can just double spot check to make sure those add up. K plus n minus k plus 1. Right, that equals k plus n minus k minus 1, which gives us our final degrees of freedom of n-1. So we know we have that correct. Our mean squared error was equal to the sum of squares regression divided by k, sum of squares error divided by n minus k plus 1. And then we could calculate our F value by taking our MSR divided by our MSE. Right? We're essentially saying if this is the same as error, then if you divide that, it should equal 1. If the value is much bigger than 1, then the mean squared due to regression is much bigger than the mean squared due to error. And we can calculate the size of that difference and compare it to an F distribution. Well, we're going to have a similar setup for the completely randomized design. But now, essentially, we would have two different pieces, right? One formula right here is giving us the scenario where the sample size for each group can vary, okay? And the next scenario is where the sample size from each group is fixed. Right? So that n is constant. And we could even go one step further with this formula. Let's do that. Okay, so if all these n's are the same exact value, then we would get the summation I equals 1 to t, summation j equals 1 to ni of yij minus y bar dot dot squared. Okay, so that looks like a total sum of squares, right? Because we have our observation, minus the overall mean, and we're squaring it. That's a total sum of squares. We can partition it into two pieces. When all ni's equal n, then that equals n times the summation I equals 1 to t of your y bar I dots minus your y bar dot dots squared plus n minus 1 times the summation I equals 1 to t of our SI squareds. Okay, this piece here is our sum of squares due to treatment. And this piece right here, that's our sum of squares due to error. From here, we can set up the same exact Anova table that we did before, but just under the context of a completely randomized design. So what we do is we set up our Anova table in this way, right? So essentially, we're taking each of these pieces and we're plugging it into the Anova table. Okay. So remember that n is equal to the sum of all the ni's, I equals 1 to t, right? So that's your total overall sample size. All right. And the Anova table that I've created here is also under the scenario where we have equal sample sizes. Let's write out the Anova table when we don't have equal sample sizes from the line above. Okay, so we have source, degrees of freedom, sum of squares, mean squares, F, and our p-value. Okay, so our source here, you have the error that's due to the treatment. You have error in total. The degrees of freedom is t minus 1, n minus t, n minus 1. Our sum of squares will be the summation I equals 1 to t of the ni, y bar I dot minus y bar dot dot squared. And then summation I equals 1 to t, j equals 1 to ni of our yij's minus our y bar I dots squared. All right. Remember, our mean square is our sum of squares due to treatment divided by t minus 1. And our mean squared error is the sum of squares error divided by n minus t. Our F value is our mean square due to treatment divided by our mean squared error. And the p-value is the probability that our test statistic is greater than the F value, where we have our numerator degrees of freedom is t minus 1, and our denominator degrees of freedom is n minus t. Okay, so this is just being able to set up the Anova table. But what we've learned in the previous chapter still hold. You can do an overall F test, which says, is there a difference in the treatments on the response, right? So you have multiple treatments and you're just asking, do all the treatments work similarly or do they possibly work differently? And so you'd set up your Anova table and do that overall F test to find out if you think that the treatments perform similarly or are some treatments superior to others. All right, I hope you learned something today, and I'll see you in the next video.